Hey everybody, and welcome back to Algebra 2 Online. So the plan for today is to basically just show you how we go about solving log equations and inequalities. So we've been building up for a while in these past few videos, like even just what a log was, and last video we did the really important stuff on the domain of logs, which will show up today. You can see it right there. And there's basically two ways you do this. You can either get a problem like this one, where you can get the same log, so same base, this is like a base 12 log on both sides, and then you can just cancel it. It's literally like those, if 2 to the x equals 2 cubed, then x just has to be 3. That kind of trick, where you can get that same thing on both sides, and you just kind of ignore it and cancel it and work with the insides. That can still work here. Or you basically just have to use inverse operations like we would do over here. So I'm going to just go through a few examples today. Some definitely get a little bit weirder than these ones. And so let's just get into it. So this one's just like the kind of first case up here. And you can absolutely just cancel the log base 12 part. So in order for those logs to equal, you need this quadratic to equal 3x. And so then it literally is now a chapter 4 problem, and you just go and solve this quadratic. So it's a nice one, factors. And so x would equal 4 and negative 1. But you have to be careful. Remember, logs are not defined everywhere. So 4 and negative 1 may both work, but you have to check them, okay? So 4 is definitely defined in here, log base 12 of 12, okay? And then here you're going to get 4 squared is 16, 16 minus 4 is 12, so you're getting the same thing. So that one's good, okay? Negative 1, though, if you plug it in right there, you can see it's not going to work because log base 12 of negative 3 is not defined, right? We can't take the log of a negative, so that thing we throw out, and we just take that one. So that's the part you have to be really careful about. Just knowing that the domain of those logs is not all reals, and so it's going to throw off answers like it did here sometimes. All right, so our other kind of problem that we can get is one like over here. This one, the way you would solve it is literally just inverse operations. The inverse function, 2 log base 2 of x, is 2 to the x, right? So just kind of this idea, like you have 2 to the x going that one way, and then the other way you have log base 2 of x, right? So we're going to literally just do 2 raised to that log on both sides. Well, 2 raised to the log here, and then 2 raised to 4 here. So think of these things as exponents, right? So these are my bases. So the way I set that up, right, if I picked 2, it should cancel that log, right? And I should then have x is less than 2 to the 4th. So x is less than 16. And that is almost correct. All right, but you have to think about the domain. So the domain for a log, right, is that the inside just needs to be greater than 0. So you need to factor this in with that answer. And so my final answer is just going to be anything bigger than 0, but less than 16. Anything in there should work. So these kind of represent the two different types of problems that we can get with logs. And I just kind of want to go through some more examples with them and kind of show harder examples from this point on. All right. So this one, same base log. So you don't need to do anything really with the log. You can just cancel it. And basically it turns into not a quadratic. It just turns into an inequality. But one you're going to have to be careful of with the domain, right? So solving this inequality, you would get that x is less than or equal to 1. And you gotta do more than that, because that is like, in this problem, I would say that's like a third of the way done, because that solves the problem, but for the domain stuff, I'm going to try to make it really big. For the domain, we need 12 x plus 5 to be greater than 0, and also we need 8x plus 9 to be greater than 0, right? So this one, these are just each of the two logs, right? So you get negative 5/12, and here you get negative 9/8, okay? So then what you do is you go through and you look at these three inequalities, and you basically have to work for everything, right? Like, you can't just satisfy one of these and call it good. You need to work for all three of these inequalities together to be a solution to this problem. This number right here is more negative than this one. So this one is not going to be useful in my answer, right? I can kind of show it on a number line. So if I have a number line here, let's take this one in green. So I've got got negative 9/8 there. So anything in there is that green one, right? And then maybe we'll do this one in purple. So negative 5/12 is less negative, right? And so, and then my answer over here, just keep the blue, I guess. We got 1 somewhere over here, and we fill in that circle this time, and then we go down. And so those are sort of my three inequalities that all have to be satisfied. But you can see that, like, in this region over here, right, there's some negative numbers, like negative 1 will work in the green region, right, this one. But negative 1 does not work in the purple one, right? So negative 1 will work over here just fine, right? You literally are going to get 9 minus 1, or 9 minus 8, which is 1. But here you're going to get negative 12 plus 5, which is a negative number. So this one is not satisfied by negative 1. So what all that means is basically this is useless. I don't need that one, right? What I need is definitely the solution, right? But then this is the more restrictive thing, and it's what will work for all of them. So, you can kind of see that the final answer would be that to that. It's like the overlapping region of all three of those up there. So, my final answer is negative 5/12 is less than x, which is less than or equal to 1. That's it. All right. So this one, I get a lot of answers that are close, but they're kind of forget one really important thing on this one. So this one is kind of like this example where we just use inverse operations. Whoops. So if I use inverse operations, I'd have to use e, right, to cancel natural log. So e to the natural log of x squared will cancel, and then e squared. So these cancel, and they reduce down to x squared is less than e squared, right? So then I would you have a quadratic, right? It's a nice one. It factors into x minus e and x plus e, right? And any of these quadratic inequalities, I would always recommend you plot the roots, which in this case are minus e and e. And then you make your rough sketch. And we want it to be less than 0, right? So we want this chunk down here, which means that it's going to be an and inequality, right? The solution to that part is just going to be negative e is less than x, which is less than e. And that is close to the right answer, but students a lot of times get caught up in solving all this that they forget the domain, right? You need to check that domain, so important. So in this one, you need x squared to be greater than 0, okay? And so, if it's another quadratic inequality, right, we have x squared looking, something kind of like that. And this is the part students a lot of times make a mistake with. X squared is almost always greater than 0, and so what they might do is they might say all reals, but it is not greater than 0 at 0, right? At 0, it is equal to 0, not greater than 0, right? And so the domain is all reals, but x equals 0. So what you get as a final answer is this thing, right? But x can't be 0. That little extra piece needs to be there. And I actually have a graph of this one. So the blue line is 2, y equals 2, right? And this thing is natural log of x squared. And you can see this is negative 2.71828, blah, 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 blah. That thing is negative e. And then 2.71828, blah, 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 is positive e. And so the red curve is less than 2 between negative e and e. But then what's going on, like after we studied our rational functions, we know that we can get these weird vertical asymptotes in graphs. And that is actually what's going on right there. That's the not equal to 0 part. So it's basically just getting infinitely close to x equals 0, but it doesn't get to x equals 0. All right. I just want to do one more. All right. So it is just one big nested sort of log equality. And I would solve this one just by using inverse operations. So you have just log here, and the base is not written. And we know from that other video that that's a base 10. So use base 10 log to cancel that one. And if you do that, then you would, cancel that thing. You're going to get log of 2 plus log base 2, x plus 1. And then over here, 10 to the 0 is 1, right? And then you just keep going. Cancel this one, right? This is also log base 10 because I don't write the base 10, or I don't write the base at all, and that is a base 10 common log. So here again, you're going to cancel now, and then you'll get 2 plus log base 2 of x plus 1 equals, and 10 to the 1 is 10, right? So you're just balancing this equation. You're just doing something on this side. You're doing the same thing on this side. I'd combine these, right? So I would just say, well, if that's just now going to equal 8, right? And then same thing here. So you have a log base 2. Just use inverse operations. The inverse function is 2 to the x. So 2 to log base 2 should cancel. And now you would have x plus 1 equals 2 to the 8th, which is 256, right? And so then x would be 255, right? And you have to think about domain. So that's already probably feels like a lot of work, but you have 3 logs here that you have to check the domain for. So honestly, we're not even like halfway done, I would say. So for this next part, domain, got to do this with all the logs. I'm just going to literally go through each log function, and you always just take the inside and you just set it greater than 0. So this first log, x plus 1 needs to be greater than 0. X just needs to be greater than negative 1. That thing is definitely greater than 1, so it's going to be fine there. So this next log, that's the inside for this log, right? So now I'm just going to be like, okay, 2 plus log base 2 of x plus 1 needs to be greater than 0. So log base 2 of x plus 1 needs to be greater than negative 2. And then I could just use inverse I can just use inverse operations. Do 2 to this side, 2 to this side. You're going to get x plus 1 needs to be greater than 2 squared is 4, so negative in there would just be a 1/4. And so then x would just need to be greater than minus 3/4. Okay, almost done. So one more log to check. Okay, so this outer log has this blue thing as the inside. And I should also say that this number is also clearly bigger than that, so it's going to work in that middle log. Okay, and so for this last one, you need log of 2 plus log base 2 of x plus 1 to be, greater than 0. Okay. Kill off the outer log with a base 10. So then you have 2 plus log base 2 of x plus 1. 10 to the 0 is 1. So it has to be greater than 1. Minus 2. I'm running out of room. So if you minus 2, you get negative 1. And then kill that log with a base 2. So then you have x plus 1 now is greater than 2 to the negative 1 is a half. And so then minus 1, you get negative a half. So basically what you have to do is you have to take your answer here and you're checking it against all 3 of these domains, right? This 255 is bigger than this negative number, and this negative number. And so it actually will work. That thing would be perfectly good. You can also just take this number, plug it in to x right here, and then just pop all that into your calculator, and you can just see that it should equal 0. So that's another way you could do that one.